Okay, hopefully everybody can see MONAI. Welcome to the MONAI Bootcamp.
We can, yeah.
Super, okay. So my name's Ben Murray. I'm a researcher at King's College London. I'm also, I've been involved in the MONAI project since the start of it. I've been largely focused on the design philosophy and the kind of high-level design of MONAI and the architecture, how the architecture realizes from that design. But occasionally I get my hands dirty and write a bit of code as well. And I also, my day job is working on deep learning, and I use MONAI for pretty much all of my projects. So I do eat my own dog food. What we're going to cover in this initial section will hopefully set you up for the rest of the day. We will take you on a journey from what we hope you already know, which is some working knowledge of PyTorch, around the features of MONAI and how we extend on PyTorch and why MONAI looks the way it does relative to PyTorch. And we'll do this through lots of hands-on examples. So you can go ahead if you want to follow along. You should be able to by setting up yourself for Google Colab. And what we'll cover is we'll cover the way transforms work in MONAI and what we've done with them, dataset loaders and datasets, and some nice features that we've provided that really solve some of the recurring problems when working with medical imaging data. And also we'll focus a little bit towards the end on network components. I give my mouse the right focus. There we go. So if you want to follow along with Google Colab, hopefully you already have got that up and running. If not, I'll dwell on this slide for a minute or so to give you time to do so. So the important thing will be make sure you change the runtime type to GPU. That otherwise nothing is going to work very well. And once you've done that, you should be able to run this command. This NVIDIA SMI will show you what kind of hardware that you have access to. I'm actually running this not in Google Colab, but in Jupyter Notebook. And if I run this for I won't need to run this, sorry, because I already have that stuff set up. But I'll run this command and we can see what kind of GPU I've got here. It's quite, it's good for a laptop. So do let people know. There should be people in the chat who should be able to help you with that if you have issues with getting yours up and running. So let's get started with MONAI. First of all, tell you what it is, although Michael has already done a good job of that. But just to frame the discussion, so MONAI is a PyTorch-based open source framework for deep learning in healthcare imaging, part of the PyTorch ecosystem, which is very nice. What does that actually mean, though? It means that we have some ambitions for this that we really want to fulfill, and we want you all to help us do this. Primarily, we're looking to develop a community that spans academia, industry, and because, I mean, these days, there's a lot of academia that goes on in industry, and there's a lot of industry that's sort of fostered from academic environments, and as well as providing tools which are useful for clinicians and clinical researchers to really have a common foundation from which we can build. And that's important because science is at least partially about reproducibility. It's quite an important aspect of it. And one of the things we really hope MONAI does is make it easier to reproduce consistent results. We are always trying to adopt in and reflect the state of the art. And that means in terms of facilities for training in challenging environments, such as when you have large amounts of volumetric data, and also providing networks that reflect the state of the art in terms of benchmark beating and the architectures that people care about at the moment, and as well as the workhorse architectures, which are very important for sort of maybe clinical adoption requires a little bit more proven time under a particular architecture. So, for example, even in a world of transformers, UNets are still highly useful. And provide overall workflows for healthcare imaging. And really to speed up researchers as well, because MONAI core is very much focused on researchers being able to innovate rapidly and do their research and not get caught up in the messy details of engineering things where there's already a best practice way of engineering things, or maybe even more than one best practice. But to not be suboptimal just by not taking advantage of those state-of-the-art features. So here's a typical MONAI end-to-end workflow. We might start off with some nifties or some DICOMs. We'll want to transform that data. In order to transform that data, we will have to load that data and treat it as part of a data set. We will have to have that data go into a model, and that model is typically trained by running it with an optimizer of some kind that's optimizing the model according to losses that we have defined for how our model should train. And then subsequently, the learned weights of those models can be used in an evaluation context, and you can visualize all of your nice results and publish papers or potentially help clinicians making decisions and saving stuff out at the end as well. And MONAI basically helps you with all of these, and that will kind of walk through this chain to a certain extent as part of this presentation. So why do we need MONAI when there's already PyTorch? The answer is that probably, as with other domains out there, there are specific needs for biomedical applications that aren't met by PyTorch. PyTorch provides you with a lot of building blocks, but if you are doing something more specialized, typically you have to then take those building blocks and make something specific to your domain. And that's very much true of biomedical applications. And it's really focused around the data that we have to deal with. Image modalities really are quite specific. They're really very different from your typical kind of photographic images or video that one is dealing with. In particular, when you're looking at MR data or CT data, you're dealing often with very large volumes of data. And a lot of the assumptions that one makes when dealing with 2D images a la ImageNet simply don't hold when you're dealing with medical imaging data. We provide a lot of first-class support for the data formats because that's something else that people generally will struggle with, particularly some of the more interesting quirks of DICOM. Those of you who work with DICOM know what I'm talking about. And we try to support that as much as possible. And there are network architectures which are sort of specific to biomedical applications. In particular, when you're looking again at sort of handling 3D data as opposed to dealing with data as a series of 2D slices. And there are a lot of transforms which are specific to biomedical applications as well. Providing all of these helps something that really may be less so now than it was 5 years ago, but something that was the bane of deep learning research's reproducibility, people publishing papers where they didn't provide even the code for the network that produced the results. This sort of thing now, I think, is increasingly frowned upon. And as part of a first-class piece of reproducible research, you should be able to provide everything such that it can be downloaded and run and reproduced. And MONAI certainly helps with that. And yes, the library of networks and losses and transforms and so on is very much community driven. And we invite people to come get to grips with MONAI and help us extend it. And we provide a lot of baseline implementations to speed people up. That's not to say you absolutely have to use our stuff. You can it's definitely not a library that makes you do things the MONAI way. We very much are a PyTorch library, and you can pick and choose the bits that you need if you're adapting across from another, from for example, a PyTorch model that you have built or that someone else has built, and you can cherry pick whatever you need, or you can go the whole hog and use MONAI components from start to end. It's absolutely your call. And I've just talked about all of this, so I'll just go over this one very quickly. So we provide a lot of direct support for loading and manipulating biomedical file types. We provide a lot of transforms when you've loaded that data. We provide a lot of componentry at the network level that's specific to 3D architectures and losses for biomedical applications. And we provide a lot of ready-made components that allow you to train and validate your networks efficiently. So I think I've touched on this 2 slides ago. So again, I'll just quickly touch on this. So we think that we are contributing to reproducible data science. Obviously, you guys are ultimately the judge of that, but we do want your feedback, and obviously it helps if you can tell us why you don't think it's contributing to reproducible data science, because it's one of our goals. We think we do help, and we try to improve all the time with every version, but we provide a common underlying framework that really aids in comparison and interoperability. You can pick and choose, as I've said, your specific pieces that you need from your research or your clinical needs, and you can integrate them with MONAI, but you can also write them in such a way that they can be contributed to MONAI, and then people will use your code, and you are then contributing to reproducibility in data science as well. And we provide a lot of reference implementations of networks, particularly designed to replicate specific papers and specific results. And you'll see that if you look through the library of networks that MONAI has to offer, we have highly configurable networks, but we also have networks that are specific to result reproduction. So I've alluded to this already, but I'll go into more depth now. So we explicitly designed MONAI to be modular and light and flexible. All of the elements of MONAI are individual modules that can easily integrate whatever you want to use, whether you want to use data loaders, data sets, transforms, network layers. You can use any of those in isolation, or you can use all of them together. It's entirely up to you. We provide, on top of all of that, some powerful workflows that you can plug into if you want to set up your own, some best practice, robust training and evaluation, or you can roll your own. That's fine. And we provide a lot of rich examples, and we provide a lot of demos and tutorials to demonstrate all of this. And we invite researchers to contribute their implementations. I am repeating myself somewhat, my apologies. We also provide a lot of implementations based on the state of the art. So we provide some sophisticated dataset caching mechanisms, as you'll see. We provide support for COVID-19 image analysis. We provide a number of model parallel execution modes, federated learning, and other things. So here's the architecture presented in a nice diagram. At the bottom level, we've got all the componentry as discussed. We've got then on top of that, workflows that you can use to do various higher level training evaluation loops. We've got a lot of examples that you can that are built on top of those, and then we've got these important and novel features that really aid people in getting to the forefront of research in those topics. And again, you can adopt MONAI at any level of this architecture. So The design philosophy of MONAI that we all agreed on at the start of it was that it should look as much as possible like PyTorch, because that allows us to do everything that I've said. It's additive on top of PyTorch. So we do extend classes, but where we extend classes, they work identically to the underlying PyTorch classes, but they've added some bells and whistles on top that we have found useful over time. As I've said, it's opt-in and incremental, and it is collaborative, and we are so PyTorch ecosystem friendly that we are part of the official ecosystem. So for the rest of the slides, this is what we're going to focus on. We're going to focus on answering these 6 key questions. First of all, what transforms are available to you? We will go into that in detail. What do we need to do if there are no transforms that suit our needs and we need to write one ourselves? How do we create data sets using those transforms? We'll look at MONAI dataset itself, and we'll look at various extensions to dataset that do really nice things like providing caching for large and unwieldy datasets. We provide as well some datasets that wrap up and make easy to access various open source medical datasets and challenge datasets. And finally, we'll have a look at these network components and networks as discussed. So any questions before we go any further? Let's just have a quick look at Q&A. Oh, MONAI Discord, I think that's been covered.
Yeah, the only one that I see, someone asked whether there were any MONAI metrics for image regression problems in Zoom chat.
Yes, I could not list them off the top of my head. I do recommend, if I can just get this bar to go away temporarily, go away bar. Thank you. I do recommend very much starting at the MONAI documentation, which is comprehensive, constantly being revised, and very much subject to feedback. So that would be a good place to start for that, or maybe someone with more specific knowledge could go into details on that on the Discord.
Oh, yeah, and I think that was actually one came up in Zoom chat. Kindly list resources and infrastructure for starters, please. Someone else also asked about the installation for a Conda setup. In the GitHub repo that I linked to that we're basing this off of, at the very bottom, there's an install a local environment instruction list that talks about how do you install things for MONAI core, MONAI label, MONAI deploy. So if you click on MONAI core installation, you can kind of follow that guide for setting up your environment. We don't have a YAML or requirements text file that I have in this repo, but there are some other ones within like the MONAI repo of depending on how you want to set up the environment. So I encourage you, I'll put those links in Zoom and Discord as well. So if you are setting up your own environment, take a look at those documentations.
Super, thank you.
Cool.
Okay, so let's first of all look at importing. There'll be a few imports that we need to do to have everything that we need for going over datasets and transforms and network components and so forth. I believe the link to the repo should be in the email, but I'm sure someone can post it there. By the repo, I presume you mean intro to MONAI notebook. Cool. Okay. So here we are. I wouldn't bother trying to memorize this. It's in pretty much every example that you'll see in any of the tutorials, and it's also here. But we break MONAI down into lots of different components. You'll see we are going to be bringing in some data sets and data loaders here, including some clever ones that do a lot of more complex management during pre-processing. We're bringing in some transforms that will be used for actually performing our pre-processing. We're bringing in some data sets as well here. I'll just run that now. There we go. Okay. So if you're running along with this session, then we'll just make sure that everything's up and running and working. If I just run this print config, you'll see the MONAI version, a few other important versions. Unfortunately, just running off the screen. Yeah, there we go. Okay. And that indicates that your MONAI setup is healthy and ready to do some data science. So let's start off with transforms. We provide a lot of transforms for training for medical imaging data. This is one of the areas where really there is a lot of need for support, because although obviously here we're looking at some images which are two-dimensional, typically I believe these are histology images. And if they are, then they can typically be much larger than typical images. So you might need some patch-based transforms. And if they're 3D data, of course, then typically networks cannot necessarily run on the full volume. So we might take patches for those. But also because the data is not your typical RGB 3-channel data, there are different kinds of transforms that you might want to apply to it. Here, if we just run from left to right, you can see the original images. You can see that here we are applying a rotation to the image in the middle, and on the right, we are applying some kind of 3D deformation or 2D deformation to the image, probably 2D deformation. And you can see as well, this is a semantic segmentation problem. So we have the image data itself, but we also have some ground truth labels that we're looking at here. And if you do semantic segmentation, you typically need to support multiple channels of inputs into your network. So with all the transforms that we've implemented, we provide them both as array transforms and as dictionary transforms. Now, if you're familiar with various different libraries for pre-processing medical imaging data, and there are a few of them out there, libraries tend to either be array-based in their design, or they tend to be dictionary-based. And if they're dictionary-based, then you'll provide a dictionary of inputs, and you'll provide a set of keys that name those inputs. And you have to tell the transform which keys it should pay attention to, and it will ignore all of the other keys. And you'll see why this tends to be something that people use. We provide a lot of support for both 2D and 3D, and we provide that support such that you can run your networks in the way that you might be used to if you're using PyTorch, through a composition of an array of transforms. What should I say about that? Yes, I've essentially said that, and we'll have the middle parameter. We'll have some examples that will clarify all of that. We split our transforms up into roughly 6 categories. We've got transforms for cropping and padding. We've got transforms for intensity, transforms for performing I/O. So, for example, loading nifties or loading DICOM. We've got some post-processing transforms, transforms for manipulating the data spatially, and useful utilities such as adding the channel automatically to your 2-dimensional data or your 3-dimensional data, so that it's in the form that data science generally expects when doing pre-processing. So specific to medical domain, we provide load image that supports all of the different specific formats that I've discussed. It's often the case that the data will be in various in spacings that are not necessarily what you want. So one of the things that people often tend to do is they'll take anisotropic data, which is typically your X and Y is different from your Z. So your in-plane data is different from the gap between slices of your data. And you might want to reorganize all of that to a common spacing. If your data comes from, say, for example, a collected data set of different scanners and they have different resolutions. It's often the case when you're looking at challenge data. The ability to reorient the data to standard orientations, providing noise to the data as a form of generalization, which is a very important thing to do when generally training with small amounts of labels, which is typically one of the enduring challenges of semantic segmentation in the medical setting, that we're working with a somewhat of a lack of ground truth. Normalization methods and scaling and cropping methods so that the data is in sensible ranges for the network to learn with. An affine transform that allows you to perform multiple spatial operations simultaneously, and then elastic transforms in both 2D and 3D, which again is another very powerful form of augmentation and brings generalization into your network. So we'll start off by creating a toy data set and a temporary directory for us to play around with these features. And we'll just be looking at spheres today rather than anatomy, but it should demonstrate everything that we want to demonstrate. So let me just run this. Okay. Oh, I'll just talk over this code. So here we are. We've got two keys here that we care about. We've got our image data and our segmentation data. You can see how we're making a temp file here. And then we're going to go through and we're going to generate 5 images. And they're going to be 128 by 128 by 128, I believe. And we save out the image and the segmentation data separately, put them all into a big list, and then we're saving those images out to our temporary directory. What's this question here? Loading a medical data generates some meta info orientation spacing, but most transforms only take a tensor in their input via a dictionary key. How should metadata be used? So MONAI provides a wrapper. Well, it's not really a wrapper, it's an extension to a standard tensor. You can pass tensors into MONAI transforms, and internally MONAI has the option to treat them as what we call metatensors. And those have metadata that travels along with them as they go through the pipeline. And as such, all of that, that meta info is audited on the actual tensor itself, and you can go and look at it as additional fields on the tensor. And this also allows you to do very useful things like converting your transforms and getting back to your original data space. Say, for example, if you're dealing with rotated patch somewhere in a volume, you want to be able to map that back to the original image. So yes, the under the hood, MONAI does quite sophisticated things to track the metadata for you. It's a little bit beyond the scope of this talk, but there's a lot of documentation on that, and I encourage you to go and have a look at it.
One other quick question, Ben, was that someone asked, does MONAI support loading any of the following directly? So they said torch tensor, numpy array, pillow images, JPEG, PNG, TIFF. Do you want to talk briefly about data loaders?
Yes. Basically, it supports all of the usual data types. You can also just bring in tensor data or numpy data. Yeah, it's very flexible. And even if it wasn't, remember, because it's built on top of PyTorch, you could just interleave loaders from other libraries, or you could even just roll your own using a fairly, using whatever loader you want to use. whatever. Oh, I seem to be. Am I running slowly at the moment? Am I cutting out?
I kind of hear something in the background, but I don't know.
Yeah, that's what I'm hearing as well. I'm just wondering if there's people. There seem to be people on the call who aren't muted. Can everybody make sure they're muted?
I'm gonna do mute all, and then and then Ben, that'll mute you as well, though.
That's a good idea. Yep.
Then yeah, so there we go. It should, I can't unmute you, but you should be able to unmute yourself, Ben, because you're a co-host.
There we go. Okay, cool. So some of these questions they are specific enough that I would encourage them to kind of be answered in the Discord if that's possible, if there are people on hand to do that. I'll just touch on it very briefly. Yes, medical images are required in different dimensions and slices. How do you handle it? It really depends on your need. If you, for example, are doing some kind of generative network, such as a VAE, where you have a latent space, then you kind of have to remap your data to a common space and every volume must be the same size. If you are doing semantic segmentation, for example, then you might just train exclusively on crops of your data because the memory requirements are such that you cannot load the whole thing. People often will take data that's heterogeneously sized and resample it into a common pixel space. So there's many different ways that you might tackle that. Those are several of them. This question about loading CT and PET data, maybe we can get into that at the end if we've got time for questions, but I think it's a bit too specific to go into here, but maybe someone can deal with it in the chat. Sorry.
Yeah, and if you have other questions as well, yeah, we also have the Slack channel as well. That's not the Discord is sort of a Slack channel where a lot more of the developers are on. Or if you want to know something specific and you're having issues with it, always start a discussion on GitHub as well. That's another option.
Yeah.
Some of these more very specific questions, if it's like really around your workflow and data, may suit it to a different venue for it getting answered.
Yeah, I think so. Okay, so the first type of transforms we'll look at are array transforms. As I say, for some libraries, they only provide array transforms. And when I say an array transform, typically I'm talking about a transform that takes a value, typically a tensor, and returns a value, typically a transformed tensor. And obviously you need multiples of these if you're dealing with multiple channels, if you don't want to do precisely the same operations on your images and your labels. So here's an example of just a straightforward array transform pipeline. Here we only have image data, so we don't need to use the dictionary ones. And basically, you can see we just compose an array of a load image and an ensure channel first. And if we run that, there you go. You'll see we've got a class of type metatensor out, and it's of size 128 by 128 by 128 with the channel dimension first, as is expected by PyTorch. As I've mentioned, there are also dictionary transforms. I'll just wonder if it's worth touching on this because I've already said it. Yes, so basically, MONAI, every transform that's implemented as an array transform in MONAI is also implemented as a dictionary transform. So whichever suits you best, you can use, and they're all used by just passing them into the compose function. So let's just go to the example here. Right, so here we go. We've got load image D, and we provide it with the two keys. And if you remember, our keys were image and label. We can call this directly. We pass it a file name and we'll get our data, and we can just print the keys. So as well, this is something that I should also mention from the question earlier. When you're dealing with dictionary transforms, as well as the metadata going on the actual tensors themselves, you also get corresponding meta dictionaries here with some values on them that maybe I can just go off script a bit. And we'll take a look at that. So there you go. Here's a whole bunch of metadata for you that is duplicated essentially on the actual meta tensor itself. So if you want to write a custom transform, if none of the transforms suit you, there's several ways of doing that. We'll start off by writing an array one, but we'll also do a dictionary one. If your transform is simple enough that you can essentially specify it as a function, you can use the lambda transform to essentially wrap your function and have it play nice with compose and other transforms. So let's do an example here. We just want to sum the values in a given axis. So we're basically summing up everything on dimension 1, and we're returning a lower dimensional tensor. Let me just run this. So for example, we can do this if we want to look at the data. So what we do is we load the image, we ensure channel first, and then we just pass our function to lambda, which will call our function when it hits this transform in the pipeline and provides you the resulting nice image of spheres here. Let me just, yeah, okay. You can also subclass from transform if you want to. Let's do that here. So it's essentially the same operation, just done a different way. We provide this transform. Do you know, I couldn't tell you whether that is, no, yes, that's a MONAI transform. And we subclass from that. We provide an initialization method for our parameters. And in this case, we're saying which dimension we want to sum. I'll answer that in a second. And if we call this, you'll see it's basically doing essentially the exact same thing. Yes, to an extent. Bearing in mind, you don't even have to use compose. Compose is just such a pattern in deep learning in PyTorch that everyone uses compose. You can just provide a function that does whatever you need it to do exactly and doesn't even use any transforms or uses some transforms within the function. It's a little bit potentially tricky to use array and dict transforms interchangeably, but you could do it. I'm struggling to think of an instant example that I could type out to demonstrate it. If one springs to mind, I might just jump in and do that as I'm going along. But yes, I mean, you can always basically write a dictionary transform wrapper that wraps up your array transforms. You could even use lambda d for this purpose. So lambda d, for example, is if you want to perform operations on a dictionary-based data set where you have multiple keys that you want it to perform the operation on, then you can wrap up lambda d in this way. So we've got two operations here. We've got a sum width and we've got a max width. And for images, we want to sum the data because we're doing essentially an accumulative weight of pixels along the path, whereas for the segmentation, we just want the maximum value. So we can basically specify a lambda d that performs sum width on image and a lambda d that performs max width on the segmentation and put it into our dictionary pipeline this way, as you can see. And I'll just run this very quickly. And you'll see we've got this summation activity going on the actual data, but the segmentations don't sum. Basically, one value wins out. The largest value wins out. Now, you can also, as well as splitting the transforms up into function, you can also split the transforms up into whether they are deterministic or not deterministic. And if they're not determined, another term for not deterministic obviously is random or stochastic. Pick your term. So with the deterministic transforms, you'll always get the same output given an input, whereas for the same input. Whereas for non-deterministic transforms, the point is that you will get a different output each time, and you either provide some random number generation to do that, or it provides its own random number generation to do that. And MONAI provides some mechanisms to allow you to build quite powerful workflows using non-deterministic transforms. So, for example, each non-deterministic transform, I'll just say random because it's quicker. Each random transform has its own RNG instance by default. You don't always necessarily want that because, for example, if you've got multiple channels that you're performing operations on, multiple, like between image and segmentation, multiple volumes or images that you're performing your pre-processing pipeline on, you may need to essentially sync multiple transforms on the same random number generation. So you can do that by providing a seed which sets the random number generators as having the same values or producing the same sequence of values, or you can provide it a random state instance that's shared between them. And also, some of our data sets are aware of randomized transforms and can do some of that work for you, so you don't have to worry about it yourself. This is one of those features that will only work on MONAI randomized transforms and MONAI and randomized transforms that are implemented to work with MONAI. So if you're using randomized transforms from another library and you can't do this sort of thing, then your mileage will vary. So let's create a basic MONAI data set with some transforms, and we'll mix in some random transforms too. We've got our source and data source now transforms defined, so we can create our data set object now. You will use the base class MONAI dataset, which is itself an extension of the PyTorch one. And as I say, it doesn't break anything. It doesn't change any existing functionality. It just adds additional extra functionality that you can make use of if you choose to do so. And if you're familiar with this class from PyTorch, then you'll be familiar with that one as well. Just having a very quick look. I may have to, they're very interesting questions, but I realize I'm also running quite far behind. So I may try and come back to these questions at the end if we've got time. Sorry about this. Okay, so let's just have a look at this code here. So we're loading our images, or rather we're loading our image names. We are creating a pipeline that loads images given the file names and adds a channel to the start. And we pass both the image list and the transforms to a dataset object. And then we can basically we can index into our dataset, for example, and get the first image. Or we can treat it as an iterator as well. Typically, we'll treat it as an iterator. We also provide as an extension to dataset an array dataset, which allows us to use array transforms in a situation where we've got images and labels, and we want MONAI to do some coordination on our behalf to make sure that everything works correctly. And what this does is it makes use of the random state of the dataset. So datasets also have a random state under the hood to ensure consistency between the two pipelines. And essentially, as long as our operations which are shared are in order, and as long as our operations which are shared happen before the unshared operations, everything just automatically works. So if we see here, for example, in our image transform, we're loading the image, we're ensuring channels first, we're doing a random spatial crop, and then because it's image data, we want to augment it by adding some Gaussian noise to it. For the segmentations, however, we still want to load the image, we still want to ensure the channel is first, we still want to perform our random spatial crop, but we don't want to perform the random Gaussian noise. Now, the array data set will take this set of transforms for image, set of transforms for segmentations, and it will ensure that random spatial crop in both of these pipelines produces exactly the same random numbers each time, so that you don't get a crop of your image from one part of your volume and a crop of your segmentation from another part of your volume, which would be bad. If I run this very quickly, there we go. We can see some nicely Gaussian image data, and we can see we've taken the same slice of the segmentation data, same crop of segmentation data. So if you don't want to use array transforms, you can use dictionary transforms instead, and Dataset works with dictionary transforms just fine. So here you can see we've got our compose pipeline where we're using a dictionary load image for both images and labels, ensure channel first for both images and labels. Then we perform Gaussian noise on the whole of the image data. And then finally we crop, but not the segmentation data. And then finally we crop both the image and the segmentation. This is actually a bit suboptimal to do. You'd probably flip those round, but the point is it's showing that it's a bit more flexible in terms of what you do than using the array data set. But otherwise, it's essentially doing the same thing. And there you go. You can see slightly less noisy spatial crop there. But, oh, that's probably because it's set to not happen automatically every time. All of these random transforms have a default probability of occurring, or you can tune that yourself. So as well as data sets, you generally have to provide data loaders. MONAI provides, again, a data loader that subclasses PyTorch's data loader. And again, it's functionally identical to the behavior that PyTorch provides, but we add in a little bit of additional things that you can use if you want to. So for example, here we're going to use multiple worker processes to load our data. And we can do that because of the MONAI data loader. And there we go. We've got a batch size of 5. So we've got 5 images. We're running the pipeline that we defined earlier, and we've got our 5 images out, and the workers worked on each of that batch simultaneously. So what is a MONAI dataset, and how does dataset caching work? If you are familiar with deep learning, you'll know that you typically train your model over many iterations, and typically over many epochs, could be even potentially thousands of epochs, so that the model is able to find a way of representing that data efficiently. Typically, you have to see every data point many times in order for the model to learn it effectively. This can take a long time, and one of the reasons it can take a long time is that you are constantly loading data, sizing data into a common space, performing normalization on the data. And you do this over and over again every time you need that data point. And this can very much be time consuming and unnecessary. So one of the things that we've really focused on in MONAI is providing excellent dataset caching functionality so that you can make your training much quicker without having to implement what is quite an involved engineering task yourself. And we'll demonstrate 2 of them here. We'll demonstrate cache dataset and persistent dataset, but there are others, and I encourage you to look at the documentation. So every dataset has a len property, a get item property, so you know how many elements there are, and you can fetch a particular element at a given point, and also act like iterators. And we'll show here, for example, how we can specify, again, a very minimal data set. We've got just a list of 7 items. We pass that into our data set, and we can essentially just iterate over those items. So there you go. The length of the data set is 7 because there's 7 elements and items, and we get each of the elements in turn. You can mix and match MONAI datasets and PyTorch data loaders and vice versa. It depends on what functionality you need. MONAI's data loader provides quite a lot of additional useful functionality, which I don't think I have time to go into here, but you can see, for example, you can just specify batch sizes that you want out of it. But really what I want to talk to you about today, the thing that's actually very important and that typically everyone ends up using, is dataset caching. So with dataset caching, we can take advantage of the fact that a pipeline is generally a mixture of deterministic transforms and non-deterministic transforms. And if we take all of those deterministic transforms and only do them once, and then we cache the result of doing that, then all we need to do each time we see that data is we run it the first time we see it, we cache the results at that point, and then we only have to run the random subset or the randomized subset of the pipeline subsequently. And if you think about performing things like loading from a Nifty file and then converting to a desired spacing, that's quite an expensive operation. So we attempt to avoid it as much as possible. Just very quickly, yes, you can cache up to a specified memory limit. The cache dataset allows you to specify what that is. And this, depending on your pipeline, can provide a dramatic speed up. So let's start off with a slow transform, and our transform is slow because we put a sleep in it for a second. And we will just run through all the elements in this data set. And each one takes about a second. And so overall, it takes about 7 seconds. And if you're running many, many epochs, that's a significant additional cost. So we can use caching to make the vast majority of this cost go away. So as I've said, cache dataset will cache the object the first time it sees it, and then it will only run everything in the pipeline from the first randomized transform subsequently. So if we run this through a cache dataset, then what we did is we did an initial iteration, and it hadn't seen any of those data samples before, so it had to run that slow transform. But now, if we run it for another iteration, oops, you'll see we were able to run 100,000 loops of that in a very, very short time indeed. Now, obviously, this is not a realistic example. I mean, realistically, you will expect to have some randomization in your pipeline. And in the real world, there is, even if you've got a resampled data set that's in a very efficient to load format, it still has some cost to fetch it. Oh no, in the case of caching, it doesn't, because everything's held in memory. So provided your data set is small enough to be held in memory, then you're not incurring the cost of loading at all. So I'm thinking of persistent data. Not for cache, no. Although you can specify a budget for the cache. If your data doesn't fit into an on-memory cache, you can use persistent data set. Persistent dataset does something very similar, except it has a folder that it will store the data out to for the result of the cached operation. So then it will have to load the cached operation each time, but it's still not performing all of the operations that it would perform the first time it saw that data sample. And again, we can run a very quick example of that. I'm not quite sure why that was as fast as it is. Maybe because I just go back. Might just be missing something. I'm not quite sure why that was as fast as it was. Oh, mainly maybe I've already got a cache somewhere. I think I have a cache from running it
maybe you already
earlier in
had
the
it from
day.
before. Yeah.
Yeah, no, that's what that is. Sorry about
Yeah.
that, folks. Yeah, so I created one earlier, apparently. And then you can see that the cache files are there in the dataset directory. And then this will run as fast as the previous one, but you can imagine if I hadn't persisted those files, it would have run the thing, waited for a second, and then saved that data out. So now, this can be a bit of a double-edged sword. On the one hand, you can use multiple instances once you have your cached directory, and that allows you to, for example, train multiple instances simultaneously from the same cache folder, which can be nice, provided that's what you intend to do. On the other hand, you do have to be aware that you might be looking at stale data if you've tweaked your pipeline. It's possible to be essentially loading stale data, so it's good practice to clear the caching folder if you do not subsequently want to load stale data when you change your pipeline. The notebook is organized as a slideshow through the use of Rise, which is a nice library that you can pip install if you're using Jupyter Notebook. So there's a smart dataset cache as well. I won't go into it here. For the motivated reader, please go and have a look at this link. And here is a graph that shows you why it's a good idea to use it. But in the interest of making sure we cover everything, I know I'm already pretty much at time, so I need to rush through the rest of this. So common data sets, we provide wrappers that do a lot of the hard work of fetching common data sets. So Mednist and Decathlon, for example, they're stored up in AWS. If you use one of these data sets, it will download it for you, extract the data, and do everything you need to just start using it without having to think about it. So for example, here we go. That's going to take a little while to run. So I'll just, do we actually need it for an example? Yeah, okay. So we'll skip on from there for now and come back to it. It's running in the background. And also, for example, there's the TCIA dataset, which if you're looking at cancer imaging is very useful, and it can basically download and extract those data sets for you without having to navigate their website, which I've done numerous times before. Let me just stop that for now, because we don't actually need it for the rest of the presentation. Right, so I won't run this. You can run it yourselves. Basically, it will show you that the TCIA dataset can be presented to you as a dataset. So finally, network components. We've talked a lot about datasets. If there's one thing I recommend you take home from the talk about datasets, is persistent dataset and caching dataset are a lifesaver. You don't have to think about performance if you're making use of those. I heartily recommend them. Everybody who uses MONAI uses them. So if you're building networks, yes, MONAI definitely supports you in your endeavors. We provide definitions for whole networks, we provide components for networks, and we provide everything down to the individual layers in a way that is proven to be useful for people developing medical imaging networks. So we'll touch on those in a bit. So we provide blocks for doing convolution with activation and regularization, because there's a lot of very common configurations of those. We provide residual units, squeezing, excitation, downsampling, upsampling. All of these have MONAI implementations that you can use, or you can use the underlying PyTorch ones as well. That's also fine. So we like MONAI layers because PyTorch doesn't really provide you very much sort of higher level sophisticated building blocks. It really provides you the fundamental Lego bricks, and it's up to you to then figure out how you want to put them all together. You get a module, you subclass from module, and from that point on, you're essentially on your own, apart from providing convolutions, activations, and things like that. So we wouldn't say that there is absolutely one best practice for constructing networks in MONAI. If you take a look at the MONAI repository, you'll see that different networks have a different way of, have a different design and architecture essentially based on the networks. And there's no one right way to do it, but we provide a number of different examples of flexible network architectures that you can either use or be inspired from in building your own networks. It's obviously very easy to build inflexible network implementations, because you just have a great big list of layers and then how they're wired together when you perform forward. But it's non-trivial to you. Yes, you absolutely can for the model and for transforms. Yes, with very, very few caveats, which are, for example, that not all transforms can do clever things with randomization, but MONAI ones can. So yes, we provide more medium to high level componentry than PyTorch does, but that componentry is very much focused on networks for biomedical applications. So one of the things that we do is, because you often have to build network architectures that can work in 2.5D, and 3D, we provide some first-class support for that. So for example, with convolutions, you can provide the number of spatial dimensions that you want to have as a parameter, rather than it being baked into the actual operation name. So here we can create one-dimensional, two-dimensional, and three-dimensional convolutions and transpose convolutions. And you'll see that under the hood, they're the torch ones. And we can configure them as well this way, so that you can basically specify what you want, and then you call it to initialize the actual convolution. Similar with activation classes, they don't need spatial dimension information in general, but they do allow you to parameterize which activation you want to use, and then parameterize the actual construction of that. Run these two very quickly. So how do you use these components to create a network? So we'll create this our network called My Network, and we'll just use a few layers to demonstrate it. So here we are. So our network subclass is from torch module. We specify how many dimensions it's going to have, by default 3, how many channels it will have, by default 1, how many channels it's outputting, in this case by default 8, the kernel size, pool kernel, and various other parameters which are useful, such as which activation function we want to use. We have to call super on the network to make sure that the module stuff is initialized. We can then define our convolution by using conv. We've parameterized it with dims, and then we construct it using these other parameters. Similarly, with activation, we specify the activation type here, and we just pass the args in this time as a keyword dictionary. And then we do the same with pooling. We specify what kind of pooling we want to do, and we then specify the kernel for pooling. And then we provide this forward function, and that's essentially our very minimal model defined. Are you talking about the last activation function or all activation functions in the model? For this model, we're just saying there is only one activation function in this model, but we're essentially just saying we want to use a ReLU, and instead of you having to have a state like an if statement in your model that says if the user said ReLU, put a ReLU here. If the user said preLU, put a preLU here. If the user said SILU, put a SILU here. It knows about all of these common activation types, and you can just parameterize it this way. Very nearly there. So here we are. We can instantiate our network with 2D or 3D inputs because we provided a DIMS parameter, flexible kernel sizes, and it's often the case that you might want to initially train your architecture on 2D data because it's much quicker to train. Yes, MONAI plays well with PyTorch Lightning. I don't use PyTorch Lightning, so I can't really go into detail with that. It also plays very well with Ignite, and I do use Ignite a lot with PyTorch. And we actually subclass some of the Ignite classes in the same way we do the PyTorch ones, by basically not touching the existing functionality, but adding some useful extra functionality with it. So there we go. We've got a 3D network, we've got a 2D network, and we've got a network with anisotropic kernels. So you see how easy it is to configure them. And we provide a whole bunch of useful networks. We provide UNets, we provide VNets, we provide AHNets, we provide VGG nets, we provide high-res net. The list goes on. So for example, we can configure a UNet here. So this is using MONAI UNet. We can specify how many dimensions, input and output channels, the number of channels we have for each layer, and the strides for the downsampling. So we've specified essentially that there will be 3 resolutions in our UNet by providing a list of 3, a length array, a list array. Goodness me, I'll try that again. A list of length 3, which specifies how many essentially resolutions our unit's going to have. I'll just run it quick. There we go. So there we are, not too late, hopefully. So we've covered MONAI transforms, datasets, caching, a little bit of networks. What I would like you to take away from this is MONAI supports biomedical applications quite strongly. We provide transforms for it. We provide data sets for it. We provide the ability for you to use everything we have and then bring your own bits in, or bring bits of what we provide into your own models by allowing you to interchange between PyTorch and MONAI. We can use MONAI datasets. We can use the caching mechanisms because they're very, very powerful. We provide ease of use to access a lot of the popular medical imaging data sets. NNUnet, well, I think NNUnet is already in MONAI core. I don't know about NNUnet and MONAI Model Zoo. Someone else will have to answer that. I'm sorry. So we've provided layers, useful blocks of configured layers and whole networks, and you can use those layers to implement flexible networks that do what you need to do whenever you're doing biomedical deep learning, such as swapping between 2D and 3D data, and nice, useful things like that. So, questions?
Yeah, there was a few ones from up above that we can kind of just go through really quickly here. Start at this one. If a transform function that we pass to a data set needs access to a parameter or metadata, how should we pass them? For example, doing a padding if the size of the image is below a threshold.
Can I see the question? Sorry.
Yeah, it's just up above a bit. Yeah, let me. Yeah, this might be more helpful really quickly if I do. Let me go ahead and share on my end.
Oh yes,
then
please.
We can
yes.
do. I'll pull up the chat really quick. And then what I will do is. This is the question for that one. I'll just put them here instead of a list for things.
So it has access to, if you're using a dictionary transform, then you automatically have access to the metadata. Because as I showed earlier, if you use a dictionary transform, when you load the data, it will load the data itself as the key that you provided, and then it loads the metadata as the key with the suffix. But if you're running MONAI with metatensors, that data is also on the tensor itself. So you can get the metadata from the tensor. So there's a number of different ways that you can do that. Does that answer that question? Hopefully. So
yes.
does caching reduce the richness of data I could have got via different random augmentations in every epoch? No, because you only cache the bit of your pipeline up to your first random transform. So if you've got stuff that you have to do every time that's just expensive and tedious, such as, for example, resampling your data to like an isotropic 1 millimeter cube spacing, you don't want to do that every time because it's just wasted. You can do it once, that's then cached or persisted if you're using persistent data set, and all of your random stuff will get done every time, or everything past the first random transform will get done every time. So no, you don't lose anything, apart from, you could say, you lose performance gain if the vast majority of your pipeline is randomized, but I mean, it depends on the pipeline. If you need your pipeline to be randomized from the get-go, then yes, caching won't help you. But if you can do a bunch of stuff and then cache the intermediate result, then caching definitely will help you. Okay. So you can, I believe, you can run your entire compose in GPU if your transforms are loaded onto GPU with your load data. No, all the randomizable transforms can run on GPU just as they can run on CPU.
Yeah, and I think most of them are now GPU enabled.
So what happens when cache rate is less than 1? Do you mean when you don't have enough space for your cache? Or do you mean something else by that? The person who asked that question.
Yeah.
We'll come back to it. If you,
yeah.
I'm not quite sure. if I'll answer it assuming you mean that there isn't enough budget for the cache, a subset of your data will be cached. Just like with a cache, you'll get some of the benefit if your cache access pattern is helpful to you, and given that the dataset ordering is typically randomized, it just means some portion of your dataset will not need to be unnecessarily processed and some portion will. Although if you want to get sophisticated with it, if you've got a small cache, you can basically have you can specify orderings for your data such that if you're doing, for example, multiple samples for a subset of your data set, that all of that fits into cache, and then you move on to a different chunk of your data set. You can get pretty sophisticated with it. Does MONAI detect if the persistent cache is outdated? Do you know, I'm not 100% sure. You can end up with stale data with it. If you change your pipeline, potentially the data can be out of date, but I don't know enough about that. There's probably some documentation on that somewhere, hopefully. If not, there should be.
So there's a few more questions, but I don't want to run too much over time. So
no, I
we
understand.
might be able to
I'm
answer
sorry
some
about
of
running
those
over time.
in. Oh, it's okay. We might be able to we might be able to answer some of those in Discord or Zoom sort of after this, but I want to hand it over for the next section. So we can try to answer a few more of them, but again, continue asking questions and we'll see if we can get to them soon. Or if we have some more time, maybe during the hands-on piece, we might be able to answer some questions while people are kind of working on things in the background for people who are interested. But great. Thank you, Ben.
Well, thank you. And thanks, everybody. And apologies for running slightly long there.